All right. All right, so we've been through Intel exploits on Linux and Intel exploits on Windows, but of course the future is ARM. As we Mac users, Mac M series users are already on ARM, and Windows has already got a version for ARM, so there'll probably be Windows on ARM hardware and servers. So that's the future. So it's good to practice exploiting ARM. And there's ARM32 and ARM64. ARM32 is for smaller systems like Raspberry Pi. ARM64 is bigger systems like the Mac. And so the first thing is you need to have some way to deliver ARM to people that don't have it. And so I made some emulated systems. What I did was make an Ubuntu system and then emulate another system on it, I think with QEMU. And usually I chose small distributions. In one case, I emulated a Raspberry Pi. Another one, I emulated an Alpine Linux distribution. So you can have some version of Linux that would be on emulated hardware and run. So if you have a Windows system, there's a couple of machines here that run Ubuntu, and then they emulate. I think this is the one that emulates Intel or emulates Alpine Linux on ARM. And if you have a Mac ARM64 based system, then of course you already have ARM64, but you don't have ARM32 because Intel and Windows always support one whole generation back. You can run 32-bit code on 64-bit Windows, but the ARM processor supports that, but the Mac operating system blocked it, which is pretty annoying. So you cannot even turn on some kind of compatibility library and run 32-bit code. So you have to run this thing, which emulates 32-bit ARM on 64-bit ARM. And as long as you use a nice, lightweight Linux distribution to be emulated, like Raspberry Pi or Alpine, it runs fast enough. So once you get the right ARM, then you can practice exploiting them. Exploiting them, I hit a lot of problems. Like I said, Metasploit doesn't seem to be much use yet. It has some things that say they're ARM exploits, but they don't seem to work when I try using it. So I had to make very rudimentary exploits. So once you're in the ARM32 emulator, this one's emulating a Raspberry Pi, a 32-bit Raspberry Pi. Then you can make a vulnerable program, just like the ones we've seen before. This one, I made it so you can put in hex codes instead of text, so we don't have to worry about null bytes and things like that to make it as easy as possible. Um, it will then interpret it. So you compile this thing for 32-bit ARM, and you get an ELF 32-bit program. Then you disable address space layout randomization, like we said before. And now you can fuzz the program, and you have to put in hex codes. So I'm putting it and Linux commands. Anyway, this is what I put. I tend to like to end in a multiple four. So I put in 410s, 414s, 418s, 4.1cs, 420s as a pattern of what's going in. And then you get a segmentation fault. So you can run it in GDB, which does work on ARM, and then you can see what went in was 2020, 21C. So some of these letters I put in did end up in the return address. Um, and so you can examine the stack and see the data you put in, and and the return pointer is down here. Now, this, by the way, might be pretty surprising because one consideration about ARM code is that it does not have the same stack layout. It puts the return pointer before the data, theoretically making buffer overflows impossible. But what happens is the reason it works is if you're in a subroutine like test password, you cannot overflow the return pointer for test password, but you can overflow that entire stack frame and the next stack frame and overflow the pointer that's going to return from main. So you are able to find, with a large enough overflow, you're able to hit something that will eventually end up in the instruction pointer, even though they have broken the classical overflow attack that we use elsewhere. So that was the game here. And so you're able to make a exploit, but remember, you need some other tricks for this. Now you need shellcode and you need a NOP, no operation code. So what I did, here's the stack, and I found a command that I could use as a no-op that takes just loads the contents of a register back into the same register. It does nothing, but it isn't a NOP command, but I can have commands that effectively do nothing. And so you can run your dummy shell code and you can slide through the NOP sled and then hit, and I couldn't find a break command, but I found an invalid command that will crash and get you back to the debugger, which amounts to essentially the same thing. So I had to do that. Then I actually used Metasploit for this and looked through the options and generated ARM32 shellcode, which I think I was able to use here. The ARM32 shellcode actually worked. I was able to make a bind shell work on the Raspberry Pi. So they have that much. For 64-bit ARM, which you can just use the native Mac processor, then once you've got ARM64, AArch64, you can make a vulnerable program the same way, disable ASLR the same way, fuzz it, examine the stack, examine an overflow, and run dummy shell code. That works the same as what we've done. And I wonder how I made real shell code. I think I was able to get some shell code here that worked. AArch64, there's a very small list, but I was able to make a reverse shell work. I think some of the others did not. Like there isn't even a bind shell available, but I was able to make a reverse shell work here. So um, it it's a lot different, but the general principles are the same. And I just wanted to tell you that there are some projects here to get you started exploiting ARM. This will probably get easier after ARM becomes common and real pen testers are actually needing to exploit ARM. Then they'll be updating the Metasploit stuff better. So anyway, that's all I wanted to show you for this one. I don't want to bother setting it up to do it live because we've done enough of that. And I think that'll do it for today. Let me stop this recording.